Alright, welcome to the next walkthrough video. This one's on buffer overflow prep by Tryhackme. This is a important room if you're wanting to try your OSCP. One of the uh, boxes on there requires you to perform a buffer overflow on an application to execute shellcode. So this room kind of gives you that preparation by providing you a vulnerable executable, provides a VM with the immunity debugger already on there, so you can kind of get that practice and get used to doing some buffer overflows on an actual live system. So let's look at the room and the box and see how this plays out. So this one is definitely a more guided room. Everything's broken down into tasks, and each of the tasks are, especially the first one is basically walking you through the process, and then each additional task after that is going to be kind of repeating the same type of stuff to figure it out, to answer the questions, and that's just to kind of reiterate the concept and make sure that you get it, and that you practice it quite a bit. Again, this box does have a Windows VM. It's Windows 7 32-bit, and that's again to kind of give you practice on starting out doing buffer overflows. 64-bit architecture and Windows 10 would be a lot harder for someone just to get started on. First you add the 64-bit to add complexity, and then there's so many built-in exploitation prevention mechanisms in Windows 10 that would make this harder. So providing this definitely helps out. So to log into the box, we need to use a free RDP that's going to basically allow us to go directly into the box and see visually what's going on. Um, and so we'll start with that. This is log in to the server, our system, and it's starting it up there. Okay. So for this here, the next portion is telling us that we need to start immunity debugger as an administrator. This is to give it the correct permissions. So we'll right click on immunity debugger, run as administrator. And older versions of immunity's free for, let's see here. So I want to say immunity is free. Yep. Download it. So you can download immunity from immunityinc.com, and that'll kind of allow you to have that on there. There's other debuggers that you could also use, like Ghidra or IDA. IDA again has some free versions with the limitations. Ghidra, similar, gives you a GUI and kind of breaks it down. All right, so we're gonna open up the binary. We gotta get to the desktop. There's the vulnerable apps right there. And then OSCP. Try to log back in. The good part is if you lose your connection, yeah, as long as the box is still up, you should be able to get back into it. All right, once it attaches, which we keep having network disconnect. All right. All right. RDP was not working. Kept having issues where it kept dropping out. So I installed our desktop. That's not default on Kali, so you'll have to install it. And then once you get that running, then the command is basically our desktop dash u admin dash p password IP address colon port number. It'll then ask you if you trust the cert, which in this case you do, and then it logs in. So then now we have a desktop session that we can see here. So if you're running that problem, then that'll give you the ability to kind of do it a different way. I'm going to try to increase the font a little bit here. Uh, Immunity is kind of known to not really have too much in customization, especially when it comes to fonts and stuff like that. So it's harder to kind of read that. So that's about as big as it's going to go, unfortunately. So the big things that we need to look at is in the corner here it says paused, and we see that there's another program open, and if we look at this program, there's nothing seen. And so what happens is Immunity attaches to the program and basically just pauses it immediately. And this is to kind of allow you that if you need to do anything like patch where it detects for a debugger or anything like that. This gives you the ability to kind of do that. But if we want to work with this program, we want it to do things. So we're just going to go ahead and click play, and that's going to kick that off. So you'll notice the windows start updating a little bit, and we're now loading all the different DLLs and modules. And running is in the back, in the side here. Now it's no longer paused. So this program is essentially just running in the background. All right. So then the next step now is we need to connect to it with our netcat and see, just do the connection out. So we're going to open this up. So netcat to the IP address and then the port number, and it's like a terminal console, and so it says that you can type in help, and then here are valid commands: overflow value, overflow 1, overflow 2, overflow 3, so on and so forth, and then you just put in a value. So if we did overflow 1, and then did A. So it just took that. And so in a, like a real program, like an FTP program or something like that, this is a similar thing. This is, think about this in a context of similar to like a web application. These are different places that you can put input, and in binary programs, especially the ones like this, putting that input may over overload the ability or how much bucket space that basically takes, and if that overflows, then that code can execute somewhere else. So if we were to sit here and just hold all these A's, um, there's no telling, and this is kind of the more manual way to test a program. So maybe you start off with 2 A's and then 4 A's and then 8 A's, and you just go on and go until you get a crash. And they might have done stuff correctly and prevented that type of stuff. And that's what most actual console type programs should do. It also depends on what language it's written in. So if it's not written in a language where it performs its own memory management and prevention of buffer overflows and things like that, uh, then that's when you can get that executable code maybe to happen. And that's usually going to be in like C and C++ and stuff like that. Go and such like that is going to handle buffers. So yeah, I tried a bunch of A's here. We still get overflow complete. So uh, let's see what the room wants to actually put you into. All right, so type help, press enter. Note that there's 10 different overflow commands, numbered. The response should be overflow complete, terminate the connection. So it's not terminating the connection, but that's fine on our end. Mona configuration. So what they have done is they installed Mona. That's to help out with finding different portions of memory and building basically your assembly type commands to get ran so that you can jump to executable code. And so we need to, let's see here, you need to configure the working folder using the following command. So we need to put this into the bottom here. And so we're going to go copy that in here, and right in this white space right here is where you're going to put that command. And as you can see, it just ran. Okay, so that's going to load Mona, and that can load it in the background. We want to go back to our view. Since this is just memory. All right. Looks like we might be. So they're providing a basic outline here of code to test. So let's put this into a text editor, and then we can go from there. Looks like we lost network connection, so I'll get that spun up while we spin this up. Okay. Gonna install that. So it put the windows in into their own little sections and doesn't have it set back up the way it did before. Um, there's a trick to get it back. Again, you can drag these and you can have open whatever you need exactly. All right, let's look at the POC. So this is written in Python 3, and that's what your first parameter up there is. We can validate that that's our way of calling Python 3. So that's fine. That worked out. Sometimes you would need to put in a different location depending on your operating system and such. So the next portion here, what we're doing then is we're importing socket, time, and system. Then we're defining the IP address that we want to communicate with, and this is just saving it as a string. And then the port is being saved as a numerical number. The reason that you can tell the difference is because this has no quotations around it. Same thing with timeout. Prefix is then overflow 1 with a space. And what they're setting up here is what we were doing earlier in this netcat session, is that we're telling the application that we're going to do overflow and then whatever number and then provide a value to it. Then we're taking string and then we're going to add prefix, which is this one here, and then we're going to specify the character A, and that's going to start out at a multiple of 100. While that's true, then we're going to try to open a socket, and that's going to create a stream as S. Then the 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 stream is going to have a timeout set of 5, and then we're going to directly connect to that IP import, and then we're looking to receive information back up to basically a 1024 characters. Then it's going to print out a statement, and it's formatting that statement out, and then it's going to send the bytes, and it's going to put it in Latin 1. So that's going to be that string. And then it'll receive whatever comes back. If there's an exception, it catches the exception and it tells you where did it crash at. And then for the next one, it's just adding another 100 bytes, 100 days there basically, and then sleeping for a second. So this is basically just a loop to keep trying 100 days until we could catch an exception. So pretty easy fuzzer. Um, Makes it easy to kind of play with this. So first thing we're going to need to do is validate that our IP address is correct, which it is. That's fine. And we are going to try overflow 1. So this is fine. We can save this file. And we'll just save this on the desktop. Okay. The cool thing about being in Visual Studio is I can just go ahead and open up the terminal. I can validate, go ahead and get into the desktop, clear here, and then Python 3. And I'm going to run this code. So it's trying each one, 100 bytes every time. So this is again 100 characters increments, and then once we get that exception, then we know that the service crashed. All right, so it crashed basically at 2,000 bytes is what it's saying. All right, so let's look at that on the GUI interface. So if we can get our desktop to run again, then we'll be able to look at this. Perfect. So it's paused. And what we're looking for is right here in the EIP section 414141. So what that's saying is that that buffer in the execution portion of the processor got overwritten by A's. So that means that the code is getting into a spot and then trying to execute. And of course, 4141 does not exist on the memory stack, uh, or not in a place that has any executable code that works, and so that causes the crash, and then that's how we get where we're at. All right, so that's basically a buffer overflow. We caused one. We were stopped, and we're going to need to restart this program now. So we can go ahead and attach. Let's close this out then. Okay. Run as administrator again. Go ahead and get that program running. All right, we'll just stick on the CPU port. There's our. So we need to get this unpaused and running. Okay. All right, so we have an idea about where the crash happens. It's anywhere between 2,000 and 2,100 bytes. And so the next thing we want to do, uh, so you can go at this different ways. So now you know where the crash happens. We could specify like a start. So we could do like an offset. Uh, that didn't write anything. Why is that not writing anything? There we go. So we could start alpha at like 2000 here. We can also go ahead and add additional, parameters and stuff that we want to keep track of. So let's keep that IP port and time out all that stuff up there. Prefix, we'll stick there. So this is going to be our code. We'll do an offset. We're going to also add a return. Padding. We'll do a payload. And any postfix. This is just going to set up the stack when we need it. All right, and then what we want to do here is combine everything into that string, because that's what we're going to send out to it. So we got the prefix plus offset. Oops, sorry. So we want offset and then overflow. And that's going to be how many A's that we want times that offset. Yep, overflow. Then where we're going to return padding payload postfix. Okay. So prefix. Now we can take out this A because now we have that in here in the overflow. Then that's going to be return plus any padding plus any payload plus any postfix. Okay. So if we set this, we should end up basically doing the same thing, just quicker. We'll even specify this to be, let's do 1700. Let's see. Probably messed up something with the code. Let's see if it actually crashed. No, it doesn't look like it. All right, so we're good there still. What we're doing, we're sending that string, which should be the overflow prefix overflow, and then nothing at the end of that. It might not be liking some of the data in there. There we go. Okay, so we're still crashing at 2000 bytes, but now we have a lot more ability to kind of add different things here. So we can start this at 2000. All right. All right, so again, we need to narrow this down, need to figure out exactly where the crash is happening. And so this is where we're going to use Metasploit. And what Metasploit has is called pattern create. And pattern create will create a pattern of characters that when you put it in somewhere, it's going to let you know basically what exact line did it crash at, right? And so we can specify uh, quite a bit here, and that's going to be put in this payload that we're going to put into our application now. So instead of doing this portion, we're going to make that 0, and we'll put this in as payload, and we'll see how this is going to identify where exactly this is crashing. And again, we could have adjusted that offset until we found the exact number of bytes that it's crashing at, but this gives you a little bit quicker ability to kind of figure that out. If I can copy it. We're going to copy this. We'll put this in payload. We'll save that. And then we'll try this again. Yep, the program will need to be restarted. So let's just do restart. Make sure that's running. And let's see if it actually crashed already. Doesn't look like it. So what we'll do here is we're going to do the POC. All right, so the program should crash now. And what we need to look at is where in what characters ended up in EIP. And so this is right here. So that might be a little bit hard to see, but what I'd like to do then is for overflow 1, let's make a comment here. Okay, and so then that's the spot where it crashed. And so let's now figure out what that is. The room's guiding us to kind of use Mona here, so we can do that. Mona find MSP and then distance 2400. All right, so looking for cyclical patterns in memory. So it's basically looking for that pattern that we put in. It put it into find MSP text file. While that's working through that, we can also get we can also just ask Metasploit if it lets us. for this, if we do H, we can do query, and then should be able to take that, and we just need to convert this back to the letters and numbers. I'm just going to copy this and so 1978. So again, this was the portion that ended up being in EIP after the application crashed. And what that's doing is this pattern is basically overriding that position in EIP, and when we provide Metasploit that back in hex form, it's able to tell you exactly where the buffer gets filled up. So if we did 1978, right, and did instead of 100, we could change this to 1 and clear back out this payload. What we should do, let's do 77 and then 78. We should end up having to crash again, right? That's what should happen. Okay, so there's that. Let's make sure this application is running. Log back into our desktop. It's the only problem whenever trying to do this remotely. You know. All right, so it's paused. What we're gonna do is just go ahead and play this, get this running. We need to restart the service, so we're gonna restart the application again. It should pause, and then we'll play it again. Okay. All right, while that's loading, what we want to do now is anything that we add after this should get filled. So again, we know exactly where the amount of characters that need to be put in there, and then here we could put some other characters, and then we should see that representative on the EIP whenever the program crashes. So we'll run this. It's starting at 1982, and that should crashed it. So it's the 78 plus the characters that we put in, and you'll see now we have 43434343, which is all C's. So now we have an exact area where we are able to kind of take control and crash this program. So the next portion of this, right, is where we don't want to crash it. We don't want to cause this application to go somewhere where it's not meaning to. And so that's when we put in actual code. Before that, though, we need to figure out some common bad characters in the application. So in C and such, what happens is that this is a string, and usually you end a string with like a /n or a null byte or some kind of special character. And those special characters let the application know that that's the end of the text, and to close out of that process and move on to the next one. Um, so what we are going to do is we're going to ask Mona to basically generate some bad characters and let us know what those are. So let's see here in Mona. byte array and -b. This is for binary, so that we're providing what that is. And I did not type Mona right. Okay, so it says it wrote it to C Mona OSCP. And byte array text. So here's a list of bad bytes in this section that we don't want to use. Okay. So if we take this, we can now make sure that we don't have that in there. Okay, so let's copy. We're going to copy these. I have them in a format without the quotations, and we're just going to copy that. Probably good to put it somewhere. Let's see. So let's try these as payload. Okay. Oops. Okay, so we're going to try the possible bad characters here. And the reasoning for that is going to be that we want to make sure that we don't have to have these in there. So we did this. We're find the distance, EIP, finding bad characters, set the payload variable to the string of bad characters that generates. So here's our script from before. What we'll do is we'll clear out the return. Okay. And then I think we save this and try this again. So update your exploit script, send the payload variable of string of bad characters that this generates. Yep, so leave the offset at 0. So we'll just put a pound here and then put this as 0 so that we have that for later. Save this. Make sure the application's running right. We are running. Everything's fine there. And what we want to know is if there's any of these characters that basically kill the program. So it looks like we're going to be fine. After it crashes, we'll figure it out. I think I did this wrong. So leave this as 1978. We do that. We do the return as B. And payload. I don't think we need this anymore. Okay, looks like we paused. So again, we have the 4242. All right. So we need to make note of the address to which ESP register points to and use it in the following command. So ESP is going to be your stack pointer. That's one right here. This is different from EIP. The stack pointer is the next portion of memory where it's going to read and do things on. And if I remember, yeah, so it's right here. This is their stack pointer, and this is the address. And then you can kind of get a glimpse of what data's in there. So we need to copy this ESP. Okay. And then what we're going to do now is we're going to compare that with the byte array that we had before and this address, and we should see what comes out. So this is definitely doing it a little bit different than I remember going through. Uh, Again, usually I I did more of a manual process, so if a character was bad or things like that, then just kind of worked it out that way. Alright, so it is saying our possible bad characters are 07, 08, 2E, 2F, A1, A2, A0, A1. Alright, so the first character should be the null byte. Since we already removed that, make note of any others, generate a new byte array in Mona. Okay. Alright, so this is basically now having us kind of work through this. So we take these characters. That's what it looks like. So the first one should be, since we moved it from the file, Update the payload variable in your exploit. Okay. So we can take this out now. Uh, ah, there we go. All right, so we need to put in, right, and then the rest of these characters, and then I guess we play with this again and see how this goes. So it looks like 07, 08, X2E, X2F, A0, A1, A0, XA1. Save that, right? We'll need to restart this process again. Get that running. Okay. So now again, we crash the program. We have 4242. Our stack pointer is should be there, which is fine. And I think now we just put in so we put in the byte array of what we have now. So let's do that. Copy. Oh, goodness. Okay, copied it. Need to do Alright, it looks like our desktop quit again. So we'll just force it. Uh, there we go. Alright, so we're gonna run Mona again. This time what we're trying to do is generate another byte array and then work through that. So let's see here. We're gonna compare, access the location of where we have that file saved. And this time again, here's our stack pointer, so we need to copy that. Alright, so it says possible by characters 0, 1. We did not send 0, 1 as a command, so we might have to play with this byte array a little bit and see which one of these it is. So let's pull that up here. See. So again, we're copying these and putting that over here. We're trying to figure out which of these bytes is not going to basically, end up terminating our payload or whatever that it is going to end up being. Okay. We wrote that there, and then we're going to try so now it says it's 0, 1, so we'll just add 0, 1 and see what happens from that. Alright, so I think that's a good start on some bad characters. It's probably not the exact ones, but we'll have to play with that maybe a little bit and see. Alright, the next thing that we need to do then is we need to find a jump command to ESP. So what we're trying to do is jump to the stack pointer and then so then this is supposed to be all your bad characters. So it's going to skip over those bad characters and basically find a command in the stack to kind of use that. Uh, Setting a return variable to that address written backwards. Okay, so let's do this. We'll copy that over. We need to put that whole string that we had. We're just gonna check. Alright, so we're going to copy in the command from the box here. Again, this is going to find us areas in the application where there's jump commands. That could get us to the stack pointer, but not include our bad characters. So we'll put this in new immunity down here. Not copy and pasting, so I'm just going to type it out. Again, this is going to be our characters that we deem that are probably bad. Seven oh eight. Two E, two F. And A0, A1. All right. So you're looking for one that has false basically all the way across. And what this is it's showing you, you know, in this case here, in this DLL, there's the location where this jump ESP is there, and it doesn't have ASLR, which is oh man, ASLR. It's application space layout randomization. Man, so that basically sets up the stack and makes it so it's not the same every time. And in other operating systems and programs, then what you would need to do is uh, find a memory leak to get that address and then be able to call it that way. Anyways, rebasing is false. Safe set SEH is false, and then OS is false. So this is basically a good, jump point that we can call this from. And so it's going to be 62, 50, 11 AF. And if you remember from here, what we need to do is make sure we copy that backwards. So we're going to um, and I'm just going to get that information here. Sixty-two 11 AF. And then, when we put it into bytecode, then we'll have to do that reverse. That's going to look like this. XAF, X11, X50, XAF. All right. Okay. So run the following MSF command on your box. Make sure to put the L host, updating your B option with all your bad characters included. So what we're doing here is we're generating a reverse shell calling our host on our port with the exit thread, uh, exit function being a thread and any of the bad characters, and we want to put that in C format, and that's going to spit out the payload. All right, so I did that wrong. That's 62 at the end. Okay, so that's going to be our return address. So we're going to copy this. It's going to be here. Okay. So then we have our offset, we have our overflow, we have our return. We'll need to add some kind of padding. So basically, this 90 instruction is a NOP or no operations, and it just kind of gives it a ability that if it jumps anywhere in that memory space, then it'll do those no operations till we get to the payload. For the payload, we're going to need, again, we need to generate the Metasploit one, so let's do that. So MSF Venom, we're going to do payload Windows shell reverse TCP. Let's specify, that's all fine. We can keep port 888, I don't care. We'll need to put the bad characters. So again, we're going to specify the ones that we identified here. And let's put those. That did not copy over like we wanted it to. Well, mostly it did, but. So let's make that note. Okay, because that's not going to be in our payload anymore. All right, and then so bad, the bad characters. We need to specify this to be exit function is going to be a thread. So this is basically going to spin up another thread. We want to do Python and -v payload. Okay, so once we can get this, we'll copy this here. We're going to just basically paste that over where our payload was going to be at. Okay. All right. this is basically set up. So what we need to do is be able to catch this shell. So we can spawn another terminal, lvnp, there we go. We're going to save that. On our desktop, we're currently paused, so let's go ahead and restart this program. Alright, let's apparently restart our desktop and then restart the program. Okay. Looks like we're good there. Everything should be running now. We have okay. Alright, so apparently we didn't do something right. Make sure we have all this correct. String equals can't concatenate string, not bytes, to string. It just did FC, so let's see if maybe that's what we messed up on. That should be the same. Alright, so we got overflow, we got offset. That's right, return. Okay, x90 times 16, then we have the bytes. That's all there, and then postfix, and then string should equal prefix. Overflow, return, padding, payload, postfix. So what's different? Can only concatenate string, not bytes to string. Uh, that should work. That All right, after a little bit of editing, we're able to get the code to work. So the big thing was that we had to take out the byte annotation on the payloads. So if you looked at the code before, it had a B in front of this, and in Python that basically tells it that it's byte notation. So it wouldn't let it concatenate or be a part of strings. So we didn't need that in this case because we're putting these bytes and other bytes on the same string basically. So what's going to happen now is that we're sending over this text overflow 1, and then we're sending basically 1978 A's, right? And then we're putting the return address. This is the address that we found that is basically pointing to the stack pointer. And then we're putting some padding, about 16 nops. And then we're putting our payload, and this is the payload for uh, Windows Reverse Shell to connect back to my IP address on port 8888. And then anything at the end if we had to post, if we needed to patch anything to kind of return execution. When we generated this code, we generated it with the exit function of thread in Metasploit. And that basically allows it to spawn off another thread and not kill the process so that it keeps running. So on the host system here, we have the program running, everything's running fine. And what we'll go ahead and do is execute this off. And you can see that we got the shell back over here, and we're able to use that now. So that's the setup, and then what you're gonna do then is basically repeat the same thing over and over again for each one of these different overflows. So we'll change overflow 1 to overflow 2, figure out the offset that you need using the fuzzer, and then figure out the return address, and the rest of it can pretty much stay the same. So this will change, this will change, and this will change, but I mean not a lot. All you're doing is changing, whatever function that you're calling here. So I'm going to leave the exercise up to you as the viewer to do that, but this is basically the setup code. Again, this was generated from Metasploit, and it's just the Windows reverse TCP shell specifying the L host. And let me pull up that command and I'll show you again. So there it is there. So there's the payload, Windows reverse, shell reverse TCP, L host. This is going to be your IP address, whatever port that you want to listen to on. Denote whatever bad bytes that you came up with, and then set the exit function as a thread. Then the file type is C, and put that as v payload, and that's going to generate the code that you're going to copy and paste into the Python file. And I'll show you here in just a second. There you go. So that's the code that's right here. And you could do this as instead of C, you could do Python, and it'll make it a little bit easier to copy it in there. Again, with the Python version though, it's gonna add that byte notation, and that might mess you up, and that's what messed me up a little bit while I was doing it. I also just realized I'd misspelled payload. So whenever you copy and paste this in there, you need to take out all these B's so that the code works in its current form in this instance here because we're concatenating all those strings. So that should get you through this room. Again, this is a great practice. It's a great way to get introduced into using a debugger and working with crashes and trying to figure out what byte codes that you need to put in there to cause that buffer overflow to actually execute more than just crashing the service. Um, so I hope you learned a lot, and catch you in the next one.